So we were discussing before I was reminded to record whether or not we are on daylight savings time now, or is that what we were on before? uh, to which my comment is, you're not changing the amount of daylight by messing with the clock. It's just changing what time of day you get that daylight, right? Is it in the morning or is it in the evening? Well, now it's more in the morning. Is that a savings? I don't know. Um, so let's see. So sine and cosine. So we're talking about these parameters. The amplitude is multiplying the output, right? So that's that coefficient A right there, right? That's the amplitude. So, and that is a vertical shrink or stretch. If A is less than 1, between 0 and 1, I should say, then it's a shrink. And if A is bigger than 1, then it's a stretch. And that will change the amplitude of oscillation, how far you go up and down from equilibrium. The equilibrium is the line that you oscillate around, right? And you know, the reason it's called equilibrium, I guess, is because it's kind of, when you're thinking of like a spring mass system, you've got something at the end of a spring which is oscillating up and down. I see Leonardo. I gotcha. Let me make sure I note that properly. Rodriguez. Yeah. Okay. And yeah, we were just talking about these parameters for the sine and cosine curves, right? So looking at this guy here, right? So why? So there's no shifting here. There's just stretching and shrinking both vertically and horizontally, right? So A will stretch or shrink vertically. And if A is negative, you'll also get a reflection in the x-axis, right? Whereas K, the effect of K is to stretch or shrink horizontally. So if K is between 0 and 1, it's the opposite for A, right? If K is between 0 and 1, then X has got to be larger to get you to where you were before. That's one way of thinking of it. And so that's a horizontal stretch. If K is bigger than 1, then you got a horizontal shrink. And that compresses towards the y-axis, right? Let's see. Yeah. And same thing for cosine, right? So the period of oscillation is this 2 pi over k. Right. So maybe that deserves a little. Can we write on the? This is I've reset up my system back at my Palm Desert home, and let's see. All right. And I've got pencils. And I'm going to say, if y is equal to a times, let's say, sine of kx, then to complete one oscillation, we want the input to go from 0 to 2 pi, right? And so let me write that out. To complete one oscillation, we want the input to go from, sorry, that's x there, right? From 0 to 2 pi. Right, and what does that mean x does? Well, we can divide all three members, presumably k is positive here, okay? So if we divide all three members by this positive number k, we get the equivalent inequality. X is going between 0 and 2 pi over k. So that's the period of oscillation. So this implies the period of oscillation, the time, if you like, if you're thinking of x as time, period is sort of indicative of a length of time, which is also a part of speech, right? A length of time. What does that even mean, right? time is not length, but they are kind of interchangeable. You know, when you say, how far is it to San Diego? You'd say, well, it's about 2 hours, which is a period of time, not a distance, right? Period, because that's, you know, if you're traveling at, you know, average 60 miles per hour, then, you know, there's this constant of proportionality between time and distance. In any case, period of oscillation is 2 pi over k. All right. So this is the amplitude of oscillation. So these are key words: period and amplitude. Okay, so when you're talking about harmonic motion or periodic motion, sinusoidal motion, you want to talk about, you know, how long is your wavelength? Well, that's going to be 2 pi over k if the input is multiplied by k, and it's going to oscillate between negative A and A. So can we draw a picture of that? Sure. We can say here is 2 pi, and is this visible? Okay, that's better. 2 pi over k. So we're going to go from 0 to 2 pi over k to complete one oscillation, which means halfway through we're going to be at pi over k, right? And a quarter of the way through will be pi over 2k. K is 1, that's pi over 2 and pi, right? And this would be 3 pi over k. Yeah, over 2k, sorry. So we're going to oscillate between negative A and A. And so here I'm not specifying what K and A are. I could still draw the graph, right? We're going to start at equilibrium, one maximum displacement away from equilibrium at a quarter wavelength point, right? Each one of these is a quarter wavelength, right? Half a wavelength, we're back at equilibrium. 3/4 of a wavelength, we're at the trough, is what I call that. The peak and the trough, right? And the peak is up here, the trough is down there. And so you're going to come up nice, smooth motion, right? Yeah. In here, it's nearly linear, right? And then curves away from the linear back towards this linear, right? So it's like, you know, you've got these tangent lines, which, you know, this one has, well, what is the slope of that? Yeah, good question. It's not vertical, right? Sometimes people draw the sinusoid with the line going straight up at the equilibrium. It doesn't go straight up, right? It goes up at an angle. How we all doing? All right. So when we're graphing these things, this is the, you know, the stretch and the shrink, both horizontally and vertically. But then we also have the shift, right? Both horizontally and vertically. So let's go back to the book and see if, I'll bet you that's what they're going to talk about next. Yeah, so they're talking about these stretch and shrink. Okay, so then here we have shifted sine and cosine curves, right? And here they just do a horizontal shift. They don't do a vertical shift, but we could also do a vertical shift, right? And so this is a horizontally shifted sine curve. So here the period is, K is 1 here, right? Do you see that? The multiplying the input. Oh, sorry, no, I see, I missed this 2 out here. So the period is 2 pi over K, where K is 2. So it's going to be pi. And then you're going to have a horizontal shift on top of that. It's a little bit confusing here because it looks like, you know, the input to sine is just 2, right? No, the input to sine is all of this, right? And, you know, you might put parentheses around all of that to emphasize that's the input to sine, right? But, you know, as they're doing here, they get a little bit sloppy sometimes, and it's sort of understood that the input to sine is everything over here. I would say that's ambiguous. If I were writing the text, I don't think I would do it that way, but so it is. And so here you have sort of this picture of this function 2x plus 2 pi over 3 is the input to cosine. So notice here they do put all of the input to the trig function in parentheses, right? So what's the horizontal shift here? Well, to see that, you'd have to factor out the 2, right? So in fact, let me write this on pencil and paper. So here's an example of a horizontally shifted function. How about an example here? F of x is, and do they have an, yeah, they have a 3/4 out here. And it's the sine or the cosine of 2x plus 2 pi over 3. So the amplitude is 3/4, right? You don't have to do any work for that, just read it off. So we're going to oscillate between -3/4 and +3/4 on the vertical, right? The period is 2 pi over k, with k is going to be 2 here. So that's going to be, let's write 2 pi over 2, or simply pi. That means that the frequency is going to be 1 over pi. And the units of frequency are hertz, which is abbreviated HZ. That's a pi downstairs there. It doesn't look like a pi, does it? All right. So hertz are oscillations per unit time, right? Actually, per second, technically. I mean, hertz is a very specific unit. It's oscillations per second. Should we verify that? Trust but verify, right? Let's see. Do I have my OED handy? Okay. Yeah. Oh, I'm going to enter in here Hertz. The name H.R. Hertz, German physicist, used to denote apparatus used or invented, phenomenon discovered, or concepts elaborated by him. Okay. But then below that, the second definition, a unit of frequency, right? Equal to 1 cycle, 1 oscillation per second, right? So that is, it's a very specific unit of time. Okay, so let's go back and see what do we have here. Yeah, oscillations per second. And so it was sort of not explicit here that our variable was in units of seconds. But if I'm gonna call these hertz, then we'd have to say 1 oscillation per pi seconds, or 1 over pi oscillation per second. Either way, right? So then we also have the phase shift. Okay, so to get the phase shift, you're going to have to factor out the, I don't know, what does your book say about phase shift? Shall we look at that? Make sure I'm being consistent with the book. They call it just the horizontal shift here. And they say it's pi over 3 to the left, or negative pi over 3. Okay, so let's not call it a phase shift yet. We'll be consistent with the book and just call it a horizontal shift. So what would the horizontal shift be? Well, to see that, you're going to have to factor out the 2 in here. So this is going to be cosine of 2 times x minus, if you like, negative pi over 3. Do you like? By which I mean, do you see why I said, rather than saying x plus pi over 3, I wrote x minus negative pi over, same thing, right? Subtracting a negative is the same as adding. So that's just to make the horizontal shift explicit, right? So the horizontal shift, which we'll start calling the phase shift, that's going to be negative pi over 3, right? So to graph that thing, you would say, okay, I've got a wavelength of pi and a horizontal shift of 1/3 of pi. So let's see, somewhere I've got a straight edge. I'm not sure exactly where I have a straight edge. I've got a bunch of straight edges around here somewhere. But we measure up, but apparently not down because they don't have the street. They got a comma here, which the next line would have whatever. Okay, so we're the equal line of equilibrium is going to be the x-axis here, and I'm going to leave a little room to the left because we're going to have a horizontal shift, right? And I'm going to say that this is 3/4 on the y-axis. So this is the x-axis, but and I'll label it the x-axis. But and I'll caution you, that's a little bit confusing because that's not the x on the unit circle, right? This is more like the t on the unit circle, the distance that you travel around the circumference of the circle laid out horizontally, right? Okay, so let's see. I think if I go 1 inch per quarter cycle, that's going to work here. So you have, whatever your wavelength is, it can always be broken into 4 equal pieces, and each one of those is a quarter cycle, right? So this is going to be negative pi over 3. That's our horizontal shift. So we're going to be at 1 there, right? Because this is, right? So what happens if I plug in negative pi over 3 here? I'm going to get negative 2 pi over 3 plus 2 pi over 3. That's 0. Cosine of 0 is 1. Times 3/4 will take me to my maximum displacement, the peak, right? Because this is a cosine curve. And then a quarter wavelength later will be, is this going to work out? I'm wondering, let's see. So if maybe not. This is pi over 3. This is 2 pi over 3. This would be pi. And pi is the wavelength, right? So the distance from here to here is 1 wavelength, right? So let me, I didn't mark my trough here. Yeah, so this is 1 wavelength, right? So, okay, I was about to do something bad, which was assume that a quarter wavelength is pi over 3. No, a quarter wavelength is going to be a quarter of pi, which is pi over 4. So what do you get when you add pi over 4 to negative pi over 3? And halfway is going to be here, right? And what is this? This is half of pi over 3. That's pi over 6. And so what's this quarter wavelength point? Well, let's just do the arithmetic, shall we? Negative pi, so a quarter length, the wavelength is pi, so a quarter wavelength is pi over 4. So if I add pi over 4 to my starting position, what do I get? Well, I get a common denominator here. So this is going to be negative 4 pi over 12 plus 3 pi over 12. Does that work? Yeah. So that's going to be equal to pi over 12, huh? Or negative pi over 12, which is 1/4 of the way here. So I'm going to say, break this into 4 equal pieces. This one is going to be negative pi over 12, right? Let's see if I can make a pi. Can he draw a pi? Yes, he can. Okay. I suppose I should follow that with a Billy boy, Billy boy. Okay, so this is a quarter wavelength here. This is another quarter wavelength. quarter wavelength is pi over 4, right? So what happens when I add pi over 4 to pi over 6? I'll do a little bit more arithmetic, right? Pi over 6 plus pi over 4. Again, the common denominator is 12, so that's 2 pi plus 3 pi over 12. That's 5 pi over 12, right? And where is 5 pi over 12? Well, this is 4 pi over 12. This is what, 8 pi over 12? So this is 6 pi over 12, and 5 pi over 12 would be right here, huh? And then we'll be back at equilibrium. And then this distance is going to be, so we have, quarter wavelengths, right? 1, 2, 3, 4. The last quarter will take us to 2 pi over 3, right? We'll be back where we started. So our curve looks like this. Right, that's one complete oscillation. And, if you were to continue on, it would, same thing over here, goes on, right, forever. But, to capture what's going on, you need at least one wavelength, right? Either starting at a peak and ending at a peak, or starting at equilibrium and ending at equilibrium. Or you could start at a trough. You could start anywhere as long as you end where you start and you've completed one waveform. To capture the essence of what's happening. Okay, so how does that compare with what they have in the book? Which is here. Yeah, they do. They draw this, see that negative pi over 12? And here's 5 pi over 6. They don't draw the, oh, they do. Here's 5 pi over 12, right. Yeah. So they draw the two equilibria points where those are x-intercepts. And what do they say? From this information, it follows that one period of the curve begins at negative pi over 3 and ends at, add pi to that, and you get 2 pi over 3. To sketch the graph over the interval of one oscillation, we divide this interval into 4 equal parts and graph the cosine curve with amplitude 3/4 as shown in the figure. All right. So using graphing devices to graph trigonometric functions, so we need to sort of choose the viewing rectangle. Okay, well, let's give this a whirl, shall we? This is kind of fun. All right, so we're going to get in here to what happened to, I don't have GeoGebra. I did open it, but apparently I need to set the properties in my viewer to say, yeah, we're going to look at GeoGebra here. Where is it? Oh, it's not coming up on my list of options. Yeah, it's not. Let me try it again. Oh. Nope, that's not it. It's grayed out is the problem. I wonder why it's grayed out. Let's see, how about I cancel that. I'm going to say add something, add existing. Oh, you can add a shader, huh? I didn't know you could add a shader. That's crazy. Browser, I guess a window capture, right. And add existing, how about GeoGebra? I now have 2 GeoGebras, neither one of which is working. Oh, okay, I just had to bring it up, I guess. The window is minimized, and so, okay. Actually, I say okay here, but now I've got two GeoGebras, so I want to get rid of one of them. How about this one? Remove. Okay. All right. So they suggest graphing the function sine of 50x. Okay. So let's just enter that in here. So sine of, so what does the 50 do? It's going to compress, right? And sure enough, that looks pretty compressed. So I got press enter, and we can expand vertically. But you see this weird phenomenon where there's little dropouts? What's going on there? Well, you know, how many points are there on this curve? Infinitely many, right? It's a continuum of points, right? Between any 2 points are there infinitely many points on the curve, right? So is that what the software does to graph it? Does it graph infinitely many points? No, it's a finite machine. It can't do that. So what it does is it samples the function every so often and then draws a little straight line between those samples, right? So it's kind of faking it in a way. So what happens when the sampling doesn't quite work, right? So as I compress this in here, we see that, you know, the sampling gets so dense that, whoop, what happened there? Whoa, what's going on here? Yeah, this is what's called aliasing. What happens is that the rate of sampling is coincident with the period of the function, so that you sample in such a way as to make it look as if you have a lower frequency oscillator than you do. Am I explaining that in a sensible way? Maybe we need a website for this. So let's go to display capture and okay, here, and let's look up sinusoidal sampling and aliasing. Okay, sampling and aliasing. This is UCCS from EAS. I don't know. That's okay. This is the second. Sampling and aliasing, it says here. Are we looking at this? Am I looking at the right thing? I think I am, yeah. So I don't know what course this is in, but look what they're looking at. They're looking at sinusoidal signal, right? And so notice that they're using some different parameters here. They've got omega, that's a Greek letter. That's the last letter in the Greek alphabet, omega. Looks like a little W. And this is phi, which is also a Greek letter, spelled P-H-I, phi. I know there's phi beta kappa, but they don't know how to pronounce it. They're so intelligent they can't pronounce the Greek letter properly. What are you going to do? I think the proper pronunciation is phi. Where t is a continuous variable. Okay, so they're talking about MATLAB and blah, blah, blah. Okay, so I don't, yeah. So let's pick another one. So here is NJIT, New Jersey Institute of Technology. Maybe they've also got a lecture on aliasing, sampling, continuous to discrete conversion. Yeah, okay, so this picture kind of tells the story. Can we zoom in on that a little bit? So what's going on here? So the gray curve in the background is the real oscillator, but it's being sampled at intervals that are longer than a wavelength. You see the wavelength here, the peak to peak distance is smaller than the sample to sample distance. So if your sampling rate is lower than the frequency of oscillation, then you can get a phenomenon that looks like so if you were to connect the dots here, you'd say, well, this dot, that dot, this dot, the next dot, and and you connect the dots with a sinusoid, you'd get a sinusoid that looks like this purple curve. Or is that mauve? I don't know. Violet. In any case, it's not chartreuse. That would be, I don't even know. Is that, I think chartreuse is like green or something. I know, I'm easily distracted. Yeah, it's a kind of liquor, but it's also color, right? Should we say color? I think it's the liquor is called that because it's got that kind of a color. And if we go to Wikipedia, yeah, chartreuse is this green kind of color. All right, sorry, distraction. So back over here. Yeah, so that's exactly what's happening in our GeoGebra curve, right? We've got a high frequency oscillator that we're sampling at a rate which is less than the frequency of oscillation. And where is it? Here? Yeah. And so, yeah. So as I come in here and yeah, sometimes it just looks like a solid green, right? Because they're connecting the dots and the dots all just make a big mess, right? And yeah, as I come in here, the more I zoom out, yeah, so there's another place where, you get a lower frequency oscillation by sampling a high frequency oscillation. I'm trying to zoom in here some more, but yeah. Okay, I guess that's, I don't know, it's kind of freaking out on me here. Can I zoom back out? Yeah, I can't apparently. I can just delete the function. No, I can't delete the function either. I've crashed the software. Oh, there. Okay. It was having a hard time with that. Okay, so but if I put in, sine of, let's say 100x, right? Then okay, it's having a hard time again. But there are going to be places where when our zoom is such that, well, let's try zooming out. Yeah, see? Okay. So this is kind of, this is a pretty, yeah, look at that. So you get these weird artifacts of, sampling zones where things don't behave quite like they should. And it kind of depends upon, sort of hitting on the right multiple of sampling rate. And I don't know what the sampling rate is, right? Otherwise I could probably dive in on that and say, yeah, if we choose this scale with this sampling rate. Okay, so here we are. So 2 pi over 100 would be the wavelength, right? And 2 pi is about 6.28. So if you divide that by 100, you get 0.0628. And yeah, so we're seeing a wavelength of about 0.0628, right? You see that there? That's about 0.06, and then we've almost completed the waveform. But as we zoom in, yeah, you get some artifacts, sampling artifacts, right? There's a place where you get some of it, right? So it looks like a low frequency oscillator, and then, who knows what's going on here, right? But we can see that aliasing effect is definitely kicking in. All right, well, your book talks about it, so I wanted to make sure we address that issue at least a little bit. Sumatra will take us back to the book. And so they're talking about this period. Okay, so now here they're talking about a sum of sine and cosine curves. So they've got f of x is twice cosine x, and g of x is sine 2x. So here we have the cosine curve has amplitude 2 and period 2 pi, right? Whereas the sine curve has amplitude 1 and period pi. And so when you combine those, you see the blue curve and the black curve. The blue curve is the cosine, and it has a wavelength which is twice the wavelength of the black curve, and also the amplitude is twice that of the black curve. And also they're out of phase in the sense that sine starts at equilibrium and cosine starts at maximum displacement, right? So what happens when you add those up? Well, I think that's a pencil and paper exercise worth our attention. We're here at 11:45. Am I monitoring the chat? And nobody's saying anything. You're also awed by this aliasing phenomenon, which I think, if you've got a digital music device, you will have experienced this. I don't know if you all were paying attention when we went from various formats to other compressed formats like MP3, right? Is a sound format which is your files are much smaller. So there's the typical Windows sound format was a .wav file, but those were very large because the sampling frequency for a .wav file, I think, is 4,000 samples per second. Why 4,000? Well, it has to do with the human brain, right? The human brain also has a sampling rate, kind of, right? I mean, it's not perfect, but and different people have different sampling rates, if you like. But there's a certain fudge factor at a certain point. If the human brain samples at a rate, or think about the range of frequencies that you can hear, right? You can hear frequencies, I think, up to 4 kilohertz. Should we talk about that as well? We can look that up on the internet. Okay, so I'm going to close our Sumatra and go to display capture. Okay, so we're here, and I'm going to put in threshold of human hearing. Human auditory, there's a group called cochlea.org. Okay, I'll just go to the first one. It seems reasonable. Human auditory range. So infrasounds are less than 20 hertz. Right, so this is this range here. Can you see that? This is infrasound. That's subsonic, right? Out of human hearing, something that's oscillating less than 20 times per second. We won't hear it. Elephants can hear it. What's that other animal there? A mole apparently can hear those. Then we get human auditory field is between 20 hertz and 20,000 hertz. Okay, so I was wrong about the 40,000. I think I said 4,000. It's actually 40,000 is the sampling rate for a .wav file. And the reason for that is it's got to be more than twice the threshold of hearing, so you don't get this aliasing effect, right? Because your sample rate will fall into the cracks, if you like. Cats and dogs can hear much higher frequency than humans, right? I guess dolphins and bats can too. Okay, so then there's intensities. This is the amplitude of oscillation, which no risk below 80 decibels. Between 80 and 90 decibels, you start running into a threshold of pain. Harmful sounds above 90 decibels. What's a decibel? Well, wait, that's a logarithmic scale for a magnitude of air pressure, which I think we'll get into next semester, or whoever you're with in chapter 4, talk about that sort of thing. But I think, yeah, what we want to do is maybe pencil and paper here, huh? Okay, that's, I think, yeah, here. So let's go for a new sheet of paper. And talk about if you've got a function f of x is 2 cosine x, and g of x is going to be sine of 2x, then we'd like to plot y is the sum of the outputs of these two functions, right? And in order to do that, I think what we'll do is make a table of values for f of x and g of x, and then for y, which is the sum of those, okay? All right, we ready to start tabulating? Where should we start? Well, let's start at 0, where f of x is going to be 2, right? 2 times cosine of 0 is 2 times 1. And g of x is going to be 0. The sine of twice 0 is the sine of 0, which is 0. And the sum of those is then going to be 2. Okay, what's our next point of sampling? Well, what are the usual suspects? Pi over 6, pi over 4, pi over 3, pi over 2, right? Which are not evenly spaced, right? Because we're skipping over pi over 12 and 5 pi over 12. Remember that on the unit circle? Let me draw the unit circle just to remind you about that. We haven't drawn the unit circle yet today. You gotta stay grounded. Okay. So here is the horizontal axis. I hesitate to call it the x-axis because there's an x over here that collides with that x as a different object, right? But I just want to mark off the usual sampling points, right? So at pi over 4, you've got the coordinates square root of 2 over 2, square root of 2 over 2 for the horizontal and vertical. And 1/3 of the way from pi over 4 to pi over 2 is pi over 3. All right, so pi over 3 is here. Now there's a point here, which is 5 pi over 12, right? And there's a point here, which is pi over 6, and a point here, which is pi over 12. All right, so if you're talking intervals of pi over 12, you got pi over 12, 2 pi over 12 is pi over 6, right? Reduces 2/12 reduces to 1/6. 3 pi over 12, well, 3/12 is 1/4, right? 4 pi over 12, well, 4/12 is 1/3. 5 pi over 12 is the equally spaced. So all these arcs are equal here, right? Each arc is of length pi over 12. But we don't know what x and y are at pi over 12 and 5 pi over 12, at least not yet. We can, it turns out, compute those exactly, but that'll come later. But for now, we know that at pi over 6, we have coordinates square root of 3 over 2, 1/2. And at pi over 3, we have 1/2 square root of 3. Of those are reversed, right? And yeah, so this is 1/2 here, and this is 1/2 there, right? And the other coordinate is square root of 3 over 2 for each one. Okay, so what should we pick? Well, for 2x, we could choose pi over 12 because twice pi over 12 is pi over 6, and we know what that is, right? But we don't know what cosine is at pi over 12. So we're just going to stick with the usual suspects. Pi over 6, pi over 4, pi over 3, pi over 2, and see where we get, right? So pi over 6, f of x is cosine pi over 6 times 2. Pi over 6, the x value is square root of 3 over 2. Twice that is square root of 3. Sine of twice pi over 6 is sine of pi over 3, which is the y coordinate here. That's square root of 3 over 2. All right? So when we add those up, what do we get? Well, I guess 3 square root of 3 over 3, or sorry, 2 square root of 3 over 2, plus this is going to be 3 square root of 3 over 2. And what is that? Well, square root of 3 over 2 is about 0.866. Do we know that value? That should be a familiar trig number, right? As a decimal, it's approximately square root of 3 over 2. So if you multiply that by 3, what would you get? Well, 3 square root of 3 over 2 is then going to be approximately, I don't know, put an 8 here, 9 here, 24 plus 1 is 25, so 2.5. So this is approximately 2.6. So we're going up. I went from 2 to 2.6. Okay. Pi over 4? Well, square root of 2 over 2 is the cosine of pi over 4, and you multiply that by 2, you get 2. Sine of twice pi over 4 is, well, twice pi over 4 is pi over 2. Sine of pi over 2 is 1. Right? So this is going to be square root of 2 plus 1, and that's approximately, well, square root of 2 is 1.414, so this is going to be 2.414. Let's just write the 2.4. So we're going down. We went up 0.6, and then we went down 0.2. Okay. Pi over 3. Well, cosine of pi over 3, we're here, that's 1/2, right? Twice pi over 3 is 2 pi over 3, which is over here, right? So this is 3 pi over 4. If I break this into 3 equal pieces, then the second one is this 2 pi over 3. Again, counting by pi over 12. So pi over 2 is 6 pi over 12. 7 pi over 12, we don't know what's what there. 8 pi over 12, well, 8/12 reduces to 2/3. 9/12 reduces to 3/4. 10/12 reduces to 5/6, right? And those are our benchmark points. And there's a 7, or what would that? That would be 11 pi over 6. Sorry, 11 pi over 12 here. This point, almost to pi, where we don't know what's what, right? This is, I guess, 7 pi over 12, where we don't know what's what. So at pi over 3, we got 1/2. What's the y coordinate here? Well, it's the same as the y coordinate over there, which is square root of 3 over 2, right? So that's going to be 0.866 plus 0.5 is 1.366. So let's say 1 plus square root of 3 over 2 is going to be approximately 1.4. So we went down a whole unit. And pi over 2, well, cosine of pi over 2 is 0, right? Twice pi over 2 is pi. The sine of pi is 0, right? And 0 plus 0 is 0. So we're at equilibrium. Are we done? Well, let's go the next quarter circle around the unit circle, right? So the usual suspects there are 2 pi over 3, 3 pi over 4, 5 pi over 6, and then we're at the halfway point, pi. And I think some of these, well, yeah, 2 pi over 3, cosine of 2 pi over 3, we're here, so that's negative 1/2, right? And twice 2 pi over 3 is 4 pi over 3. Where's 4 pi over 3? Well, this is 3 pi over 3. So 4 pi over 3. Divide this into thirds, right? 4 pi over 3 is about here, where y is negative 1/2. Okay. So here we're at negative 1. That was easy. I'm still missing my battery. Oh, well. Nobody wants to hear that annoying man anyway. That was easy. How are we doing? Is it it's almost the 13th hour. or in elevator time, the 14th hour. What? All right, sorry. So 3 pi over 4, cosine of 3 pi over 4, that's negative square root of 2 over 2, right? And twice 3 pi over 4 is 3 pi over 2, that's the south pole, right? 3 pi over 2, where y is negative 1. Part of the reason for doing this is just to get familiar with navigating the unit circle, right? All right, so what do you get when you add these up? Well, I guess you get like negative 2, negative square root of 2 minus 2 over 2, if you like. And square root of 2 is approximately 1.414. Subtract 2 from negative square root of 2, you get negative 3.414. Half of that is negative 1.7. All right. So we went down further. 5 pi over 6, cosine of 5 pi over 6 is negative square root of 3 over 2. Sine of twice 5 pi over 6 is 5 pi over 3, which is here. 5 pi over 3. And what's the sign there, I guess, right? That's negative square root of 3 over 2 again. Oh, okay. So that's negative square root of 3, which is approximately negative 1.7 again. 73, but so these are not exactly the same, but they're pretty close, huh? Interesting. At pi, cosine of pi is negative 1. Sine of 2 pi is 0, so we're back at negative 1. Oh, so you can see a kind of symmetry happening over here. And have we completed a wavelength yet? No, in fact, the wavelength of this thing is 2 pi, so we're only halfway done. Let's kind of finish this up with GeoGebra, because it's taking this pretty painstaking, right? How you doing? Okay, there's no comments in the chat, so everybody's happy. That's what that means. Okay, all right. So not Sumatra. I want GeoGebra. Okay, and let's delete this guy. And put in our function, right? Well, let's put in the two pieces, right? So we have 2 cosine x. Oh, does that look like the right thing? Yeah, amplitude 2, wavelength pi. Do we see that that's pi? Or 2 pi, I'm sorry. Right, so right here we've completed, we're from peak to peak, a little bit more than 6.28, yeah. And here's going to be twice, oh no, sine of twice x. That's that curve, right? And then I'm going to say f of x plus g of x. Right? And that's that purple curve. If I turn these guys off, you can kind of see, yeah, that's a weird waveform. That's not a sinusoid, right? It's the sum of two sinusoids. And if you have sinusoids of the same frequency, it's going to turn out that those will give you another sinusoid with that frequency, but a shift and a stretch or a shrink. If you have two sinusoids of different frequencies, you don't get a sinusoid. You get some sort of waveform that's not sinusoidal, right? This is called additive synthesis in music technology. The idea is that you want a waveform that sounds like an oboe or a bassoon. You can approximate that kind of a waveform by adding sinusoids of different frequencies and amplitudes. Yeah. So shall we? So this is h of x. So what did we do so far? We found h of 0. Oh, let's plot that point, right? So the point 0, h of 0. That's our starting point 2, right? Then we did what? Pi over 6, comma h of pi over 6. There, oh, that turned out to be a peak, huh? Yeah, we got 3 times square root of 3 over 2, about 2.6. Yeah, looks like we're right on a peak, huh? So that's the amplitude of this waveform. Um, and I'm going to say pi over 4, comma h of pi over 4. Okay, there's that point. And then pi over 3, comma h of pi over 3. There's that point. And then we said pi over 2 in parentheses, right? We're giving coordinates of a xy point, right? H of pi over 2, right? So we're at equilibrium there. And then we said the next point we were interested in was 2 pi over 3, comma h of 2 pi over 3. It's that point. Okay, sort of equidistant on the other side. Not really, huh? Oh, did I screw that one up? Oh, I did, didn't I? Wait. Let's go back to the pencil and paper because I'm getting an inconsistency here. So 2 pi over 3. What did I say? Oh, twice. Yeah. I forgot to multiply the output by 2, right? So this should be a -1 here. I'm feeling I made another mistake with the other one. Did you see that mistake and just not say anything because you're trying to be polite? If you see something, say something. How are we doing? All right. So then how about the other one? Let me check this one as well. G of x. So 3 pi over 2. Oh, 3 pi over 2. That's a -1. Oh, sorry. 4 pi over 3. Yeah. So 4 pi over 3 is here, where y is -1/2. So this should be -3/2, right? That's not what I'm getting on my diagram, on my GeoGebra. So let's go to GeoGebra and see, what did I do here? What is this point? 2 pi over 3, h of 2 pi over 3. Yeah. And that's a point on the curve, but it looks like it's closer to -2 than -1.5. It's actually -1.87, it says here. I betcha I screwed up my pencil and paper work. Got to be careful here. So let's check it again. So if x is 2 pi over 3, then twice that is 4 pi over 3, which is here. Oh, and we're talking sine at 4 pi over 3. I said that was -1/2. Sure looks like -1/2, doesn't it? 5 pi over 3 will get you negative square root 3 over 2. Let's check cosine again. I don't know. So 2 pi over 3 is here, where cosine is -1/2, right? And twice that is -1. So that's what I wrote down here. G of 2 pi over 3 is sine of 4 pi over 3, which we're here, and that's R. Why is this not working out properly? It looks like it should be 1 plus square root 3 over 2, or -1 minus square root 3 over 2, right? And so G is sine 2 pi over 3. You double that, you get 4 pi over 3. Oh, I'm sorry. Yeah, I've got my unit circle screwed up. Sorry, my bad. So what is this point? This is 7 pi over 6 here. and this is 4 pi over. Were you seeing that and just not saying anything? So yeah, so this is negative square root of 3 over 2. And so that's what this is. And indeed, it seems reasonable by symmetry, right? These are equidistant from pi over 2, which is at equilibrium. So if you go to the left, you're up. I said this was 1.4. 1 plus, should we verify that also? 1 plus square root of 3 over 2 is equal to, this is 1.732 plus 1 is 2.732 over 2, and that's going to be 1.36. I'm getting 1.87. Damn it. Oh, yeah, because it's negative 1, not 1/2. Crap. Okay. So what I want to compute, I mean, that's correct, but 1 plus square root of 3 over 2, or the negation of that, is going to be negative 1.866 over 2 plus square root of 3 is going to be 3.732 over 2, which is approximately negative 1.86, right? All right. So that's the number, or 1.87, I guess, closer to that. So that's this number. So this is negative 1 minus square root of 3 over 2, which is apparently up here. I also forgot to multiply this by 2. Geez, I'm really screwing up here. All right, so this is 1 plus square root of 3 over 2, which is approximately 1.87. And this is the negation of that, right? Which is approximately negative 1.87. And then we go up. Okay, so let's see if GeoGebra is verifying that. Oh, we're over time. Okay, so yeah, so you see that this is negative 1.87. This is positive 1.87. So yeah, it's good to do things by hand, but the technology can definitely help you to verify that you're doing it right. Okay, so if I have 3 pi over 4, comma, h of 3 pi over 4, that's a point there, which is sort of symmetric, right? And this point is going to be 5 pi over 6, 5 pi over 6, comma, h of 5 pi over 6. And, oh, what did I do here? H of 5 pi divided by 6. Okay, so that's that. And notice that, yeah, well, actually, no, we're going to have to do all new computations for over here, right? Yeah. So we're only half done with the work here. But, you know, if we were to plot these dots carefully, you know, we'd get this part of the curve. It's pretty clear, right, how to connect those dots with a smooth curve. We'd have to make new dots over here and then connect those with a smooth curve. And maybe we'll take up with that tomorrow. Any questions before we quit?
Professor, I was wondering if you could do an extension for the 5.2 homework.
Yeah.
Thank you.
Okay, 5.2. And edit assignment settings. I can actually do this now. Let's say, Wednesdays. Yeah. The important thing is that, yeah, you just do it. So, all right. I think we kind of walked through that one all together, but there are parameters. So, you know, you have to sort of understand it. You can't just copy it in, right? Okay, great. Anything else? Oh, I wasn't showing you what I was doing there, right? So now this is, yeah, this is due Wednesday. All right, everybody, have a pleasant afternoon. And yeah, okay. We'll close it out here then. Okay, bye-bye.